Hey everyone, thanks for tuning in. Today I will be discussing vector matrix vector queries and how to use them to solve linear algebra, statistics, and graph problems. I'm Cyrus Rashton, and I'm currently a postdoc at UCSD. This video is about a joint paper with David Woodruff and Hanlin Zhu. Let me start by explaining what these queries are and what you can do with them. Throughout, I will refer to vector matrix vector queries as UMV queries for short, and you'll see why in a second. Our goal is to learn something about an unknown matrix M. Let's say that it's n by n. To make a query, we choose two n-dimensional vectors u and v. Then, when we query with this pair of vectors, we get the value of u transpose mv, and we do this many times. Choose another pair, uv, query the matrix, get the result, repeat. In general, the goal is to figure out how many queries you need in order to determine some interesting property of the matrix. I think it's a cool model. For one, we can use UMV queries to simulate queries on graphs. Here M corresponds to the adjacency matrix, where a 1 indicates that an edge is present and a 0 means that there is no edge. If U and V are indicator vectors, then we get a single entry of the matrix. This tells us whether or not a certain edge is in the graph. As another example, we can set U to be an indicator vector and V to be the all ones vector. This reveals the degree of a vertex. What I really like about the UMV model is that it unifies many previously studied queries, and there's a huge literature on other query models. I can't do it justice in this short video, but let me mention a few examples. I just explained edge and degree queries. We can also access specific neighbors of a vertex or sample a uniformly random edge by using about log n UMV queries. These other queries are local in the sense that they only access a single entry or row of the matrix. On the other hand, UMV queries are global because they reveal a small amount of information about the whole matrix. There has been a lot of nice recent research on other global queries in the context of graphs. An edge count query gives the number of edges in a subgraph. There are also cut queries, which are like counting edges in a bipartite subgraph because we get the number of edges between one set of vertices and another. We can simulate edge count or cut queries with a single UMV query. Choose U and V to be the indicator vectors for the corresponding subsets of vertices, and this gives us the number of edges. Okay, so I could go on, but instead of digressing or randomly name-dropping the authors, let me just refer you to our paper for proper references and more details. So let's get back to UMV queries themselves. We don't just have to look at graphs, we can look at any matrices and vectors, and we can study linear algebra or statistics problems. Before getting ahead of myself, I should iron out some details. I haven't really talked about what field we are working over. That is, what does U transpose MV even mean? It turns out that it matters, sometimes a lot. For graphs, it makes sense to just consider the reals. Later on, I'll also consider F2, the field with two elements. Another important point is that we assume the query vectors have bounded entries, so that the query only outputs about log n bits. We need to do this because otherwise we could learn the whole matrix in one shot by using vectors with really big entries. And this wouldn't be very interesting. Also, when the output of the queries can be stored efficiently, then an algorithm that doesn't use too many queries can be executed with a small amount of memory, for example in a streaming or distributed setting. Now that I've defined the model, let's move on to actually explaining some new results. Today I will talk about three different problems and explore their query complexities in the UMV model. The first problem involves diagonal matrices, which have the property that all non-zero entries lie on the main diagonal. The task is to determine whether the unknown matrix M is diagonal or not. If we could only use local queries, such as revealing a single entry at a time, then this would be a difficult task. We would have to look at almost the whole matrix to figure out if any of the off-diagonal entries were non-zero. In the UMV model, I will explain how to determine if a matrix is diagonal by using only a constant number of queries. This means that it is possible to succeed with 99% probability by making a number of queries that is independent of the size of the matrix. The second part of the talk will concern permutation matrices. These are binary matrices that have the property that in each row and each column, there is a single entry that is a 1 and the rest of the entries are 0. The task will be to determine whether a binary matrix is a permutation matrix or not. For this problem, we will see a situation where the underlying field matters a lot. When we compute the UMV queries over the real numbers or any large enough field, then I will show how to solve this problem with high probability by using only a constant number of queries. On the other hand, when we are working over F2, then I will prove a lower bound showing that omega n queries are necessary. The final result in the talk is perhaps the most technically interesting. I will consider approximating the Schatten p-norm of the unknown matrix M, where this norm is simply the LP norm of the singular values of the matrix. For example, the Schatten 2 norm is the square root of the sum of the squares of the singular values. These norms are important for many applications in numerical linear algebra, and they have been studied intensively in the streaming and sketching setting. I will prove lower bounds on the number of queries needed to get a constant factor approximation in the UMV model, where the bound will depend on the value of p. The reason I want to explain this result is because we develop an interesting reduction method that might have applications to other problems as well. We look at certain classes of random matrices, and we show how to simulate general UMV queries by using only entry-wise queries to the matrix. So overall, those will be the three main parts of this video. In our paper, we explore several other problems, and I would encourage you to check it out if you are interested. I chose these three topics for the video because I think they provide a good overview of the power and limitations of UMV queries, as well as some of the main techniques that come into play. So let's get moving and talk about diagonal matrices. This is a good warm-up example because the algorithm is pretty simple, but it also shows off why UMV queries can be pretty powerful. Recall that a diagonal matrix is one where all the non-zero entries are on the main diagonal, and our task is to determine if the unknown matrix M is diagonal or not by using only a constant number of queries. We are going to focus on making one query with random vectors u and v. If the output of the UMV query is 0, then we are going to count this as a vote for the matrix being diagonal. In particular, the query will definitely be 0 if the matrix is actually diagonal, and with some constant probability, it's going to be non-zero if the matrix is not diagonal. In other words, it's a one-sided tester. And we can just repeat this process a bunch of times and ramp up the success probability as high as we'd like. The only thing left to do is to explain how to choose the random vectors. We let each entry be random, except we are going to impose one constraint. We don't want the query to hit any of the diagonal entries in the matrix. In other words, we want ui times vi to equal 0 for all I, and the other entries will be random over the field. Or we can even just pick a subset of size 2 and choose between these two at random. But one of either ui or vi will definitely be 0, and the other is random. The point is that even with this constraint, we are going to touch about a quarter of the matrix. So if there is a non-zero element, then we will hit it with some probability. And then, conditioned on this, because the vectors are random, we will get a non-zero output for the UMV query. This is basically just a Schwarzschild lemma. I think we had to do a direct calculation when the field is f2, but either way, this query algorithm will detect a non-zero off-diagonal element with probability at least, say, 1 over 16. And otherwise, if the matrix is diagonal, then the output is always 0. So overall, we have a one-sided tester that succeeds with constant probability. And if we repeat it enough times, we can increase the success probability as high as we'd like. It's a pretty simple algorithm, and it shows how UMV queries being global and touching a lot of the matrix can be very useful. Next, I'll show you how to use a similar idea for permutation matrices. Remember that a permutation matrix is a binary matrix such that in every row and every column, there is exactly one entry that is a 1 and the rest are 0. And again, I'll show how to use a constant number of queries to determine if a matrix is a permutation matrix or not. Here, it is important that the queries are over the real numbers or any large enough field. We also need to assume that all entries of the matrix are either 0 or 1 even if it's not a permutation. Then, we can use a similar strategy as before. We first simply check that the matrix has exactly n ones by using a single UMV query with all 1 vectors. If not, then the matrix is not a permutation. Okay, good, so let's assume this holds. Then let me show you a one-sided tester. It will always be correct if the matrix is a permutation, and if not, then with some constant probability we will be able to detect this. For simplicity, let's assume that n is even. We start by choosing a random set of n over 2 columns. Let's call this set A. Then, we let v be the indicator with 1s in the positions corresponding to A, and u will be the all 1s vector. So this gives us the count of 1s in the columns from A, and since A has size n over 2, we better have exactly n over 2 1s. We can modify this procedure slightly to make the analysis simpler. We will make 2 queries in a row, one where v is the indicator vector for A, and another where we use the complement of A instead. By the same reasoning, both of these queries better output n over 2. So the final algorithm will be to do this a bunch of times, and then also do it where we choose rows instead of columns. So now, let's analyze the success probability. We just need to check that the probability that we see something other than n over 2 in one of the 2 queries. If this happens, we output that the matrix is not a permutation. The key property is that if the matrix is not a permutation, but it has exactly n ones in total, then there must be some row or some column with at least 2 1s, and another must be all 0s. By symmetry, let's say that it's columns. Otherwise, that's why we also do the query with rows instead of columns. Now, since A has size n over 2, there is a constant probability of it getting exactly one of these 2 faulty columns in the random set A, and this is good for us. Consider the other columns besides the 2 faulty ones, and think of them as being split up into 2 groups, the ones contained in A and the rest. One of these 2 groups has to have more 1s than the other, or they must have the same amount. The good case is when the faulty column with 2 or more 1s ends up in the group with more 1s already. When this happens, the total number of 1s will be greater than the group that gets the column with no 1s at all. And we have chosen A to be a random set of n over 2 columns, so with probability 1/2, the faulty column with more 1s will bump up the size of one of the groups, and one of the queries will output a different value than n over 2. This is exactly what we wanted, and this tells us that it's not a permutation matrix. On the other hand, if it is a permutation, then the counts will always be n over 2, so we have a one-sided tester, and we can increase the success probability by using a large constant number of queries. And that's it. Stepping back a second, let me mention 3 things. First, the permutation matrix problem is actually identical to the problem of determining whether a graph is a perfect matching or not. So that could be one application of this algorithm. Second, the same idea can be used to determine if a matrix is doubly stochastic or not, which means that the rows and columns contain non-negative real numbers that sum to 1. You just do the same queries as before, but check if the sum is exactly equal to 1/2. Finally, at a high level, we see that the crucial part of this algorithm is that we needed to be able to count, and the field had to be big enough for this. A natural follow-up question is, what if the field is f2, so that we only get parities? Then, can we still design an efficient algorithm? It turns out that the answer is no. When the field is f2, let me show a lower bound of omega n on the number of queries to solve the permutation matrix problem. To do this, I will reduce the problem to the communication complexity question of set disjointness. Here, the 2 players Alice and Bob each have a length n binary string, and they want to determine if the strings are disjoint, or if there is a position where both strings have a value of 1. It is well known that this requires omega n bits of communication, even for randomized communication protocols. Let me explain the reduction. Alice and Bob are both going to build matrices based on their bit strings, and the sum of these matrices will be a permutation if and only if the strings are disjoint. We will use a little gadget to map each bit in the string to a little 3x3 matrix. And then Alice and Bob do this for all the bits in their strings. If there was an algorithm in the UMV model for permutation matrices, then this would directly lead to a communication protocol for disjointness. But since the lower bound for disjointness is omega n, we get the same lower bound for the number of queries to determine if the matrix is a permutation when the queries are over f2. Great, so that will achieve our goal, and I just have to explain the gadgets. If Alice is a 0, then she will add this submatrix to her overall matrix. And if she has a 1, then she will add this one instead. If Bob has a 0, he will add this one, and if Bob has a 1, he will add this one instead. So those are their 4 submatrices. Alice and Bob build their overall matrices using these. And we can directly check that the sum of their matrices over f2 is a permutation if and only if the strings are disjoint. For example, if Alice has a 0 and Bob has a 1, then the sum is this matrix, which is still a permutation. Over f2, 1 plus 1 is 0, so that's why we get that matrix. I'll let you check the same thing for the other pairs 0, 0, and 1, 0. For the final case, we can look at when Alice and Bob both have a 1. This time, their matrices will sum to the all 1s matrix, which means that the overall matrix will not be a permutation. So that's the reduction to set disjointness, which proves the lower bound that we wanted to prove. Now, I'll move on to the final section of this video, which concerns querying random matrices and estimating the Schatten p-norm. After that, I will conclude and mention some open questions. Let me start by explaining a cool way to understand what happens when you use UMV queries for certain random matrices. Later on, we will build on some previous results in the streaming setting and prove lower bounds for estimating the Schatten p-norm. These results use a distribution over matrices with 2 nice properties. First, the matrices are rotationally invariant. This means that if you permute the rows, then you have the same distribution. The other property is that the matrices are orthonormal, so we call such distributions orthonormal and rotationally invariant. What this allows us to do is to generate a random matrix that really only depends on the singular values. We can build a matrix M by choosing 2 matrices U and V from orthonormal and rotationally invariant distributions. Then, we can fix a diagonal matrix sigma of the singular values. If we look at U sigma V transpose, then we get the matrix M, and the singular values are preserved. When we talk about Schatten p-norms in a little bit, we will use this property because these norms only depend on the singular values. And overall, I think this general approach can be useful for other problems that are based on the singular values as well. So what I want to prove now is a cool connection between UMV queries and a more restricted model that only looks at the entries of the matrix one by one. We show that if you have any deterministic UMV query algorithm that makes S queries, then you can actually get the same information from the matrix by using S-squared entry-wise queries. This is pretty crazy in general, but it turns out to be true when we are querying matrices M like the one I explained before, that is sampled by using orthonormal and rotationally invariant distributions. Now let me explain the ideas behind the proof. We will use induction on the number of queries S. We start with the base case, where there's only one query. Let's say that we use some vectors u and v. We can assume that they have unit norm because the algorithm can just rescale the result later. Then, since M equals u sigma v transpose, we are really just querying sigma with the vectors u transpose capital U and also with v transpose little v. But of course, capital U and capital V are orthonormal and rotationally invariant, so it doesn't really matter what little u and little v actually are. We could have just used the standard basis vector e1, which is the vector with a 1 in the first position and zeros everywhere else. In other words, we could have just queried the first position of M. This leads to the exact same distribution where we multiply with capital U and capital V, so we get the same output that really only depends on sigma. The rest of the proof is by induction, and you can find the full details in the paper. The main idea is that we can take any S queries in the UMV model, and we can simulate the first S-1 by using S-1 squared entry-wise queries by induction. And then, for the last query, we can write things down using orthogonal projections. We show how to fill in the missing information, so to speak, by making S-squared entry-wise queries in total. And in fact, we can just look at the S-squared entries in a corner of the matrix. This is powerful because entry-wise queries are easier to analyze. And we have a way to go from any S queries in the UMV model to S-squared queries in the entry-wise model. So I hope this finds some neat uses in the future. Let me now explain why this is enough to get a lower bound for approximating the Schatten P norm in the UMV model. This norm for our matrix is the LP norm of the singular values. If we write them as sigma 1, sigma 2 up to sigma n, then the Schatten P norm is defined like this. When P is 1, this is sometimes known as the trace norm, and when P is infinity, then it's the largest singular value, which is sometimes called the operator norm. These norms come up a lot in quantum computing and in numerical linear algebra. And there's been a lot of work on sketching vector norms, so it makes sense to try and understand what happens for these matrix norms. Anyway, our motivation was mostly that there was this paper by Lee, Wynn, and Woodruff that proved a bunch of results on sketching these matrix norms. They give upper and lower bounds for general sketches and also bilinear sketches, so we wanted to see what we could show in the UMV model, which is very much bilinear. To do this, we use the lemma that I just discussed. We get the following lower bounds for the number of queries needed in the UMV model to obtain a constant factor approximation to the Schatten P norm. When P is less than 4, then we get a lower bound of square root n queries. And when P is at least 4, then we get a lower bound showing that you need n to the 1 minus 2 over P queries. To give some context to these results, let me mention a related query model that is more powerful than UMV queries. This is known as the matrix vector query model. And as the name suggests, you specify a single vector v and you get the output m times v, which is an n-dimensional vector. A previous paper by Sun, Woodruff, Yang, and Zhang studies this model for a bunch of linear algebra, statistics, and graph problems, and in many ways their work was an inspiration for ours. In the matrix vector model, when P is a multiple of 4, it is known that we can approximate the Schatten P norm using only n to the 1 minus 4 over P queries. So this gives an interesting separation between the matrix vector model, which is more efficient in this case, and the UMV model, where we are about to show a larger lower bound of n to the 1 minus 2 over P. Let me briefly explain how the lower bound works. It combines the Lee, Wynn, Woodruff result and the lemma that I just explained a few minutes ago. First, the previous lower bound uses orthonormal and rotationally invariant distributions, so that's where this comes from. Then, by using Yao's principle, we can assume that the UMV query algorithm is deterministic. Their result gives a lower bound on how many entry-wise queries we need to make to approximate the Schatten P norm. When P is at least 4, the number of queries is omega n, so this means that if S was the number of UMV queries, then we can use the lemma from before to get an algorithm with S squared entry-wise queries. And putting this together, we get that we need S squared to be omega n, or in other words, the number of UMV queries S is at least square root n. For P at least 4, the lower bound is that S squared is at least n to the 2 minus 4 over P, so taking the square root again, the number of UMV queries must be at least n to the 1 minus 2 over P. And these are the two results in our theorem about Schatten P norms. The full details are in the paper, and I just wanted to explain why that lemma is useful for proving lower bounds, so hopefully you see that now. That's the last of the technical results in this video, so let me wrap up. I have explained some of our new results in the UMV model. We saw some upper bounds and some lower bounds for a few different problems, and we study many more in our paper. Overall, this idea of querying with properly chosen random vectors seems to be very useful. And for the lower bounds, reducing the communication complexity can give many nearly tight results that often match the upper bounds. Let me point out a few open directions that could be fruitful. A lot of work on graph queries is focused on finding efficient algorithms for approximately counting subgraphs such as triangles. We can simulate these results in the UMB model, but I wonder if much better algorithms can be found. Another question that a few people have asked me is whether you can determine if a matrix is positive semi-definite or not. I think this will require a large number of queries in general, but it might be possible to do efficiently if you make some assumptions on the eigenvalues. At a higher level, I would like to see new general techniques for solving problems with a sublinear number of queries in the UMV model. I'm also curious whether interesting connections can be found by looking at the k-linear generalization of UMV queries. Here, you would have a k-tensor and then specify k-query vectors. This seems like it could be a vast generalization of UMV queries, which correspond to the case k equals 2. But still, you only learned a small amount of information about the whole tensor, so maybe there are interesting trade-offs. Anyway, thanks for watching until the end. I'm Cyrus Rashton, and here's my website, my email, and my Twitter handle. If you have any questions about this video or about our results, feel free to reach out to me. And that's the end. See you later!